Green sulfur bacteria by Jaime Coverti. Green sulfur bacteria is anaerobic bacteria and is found in the deepest waters where low light is available. Due to them being anaerobic, they undergo a process of anoxygenic photosynthesis, where light energy is used to fuel ETC and create the proton gradient used to initiate ATP synthesis. Green sulfur bacteria uses bacteriophils instead of chlorophylls. These bacteriophils are A, C, D, and E bacteriophils. Due to them being anaerobic, they do not undergo the same processes with water, and instead use sulfide ions as electron donors. They use type 1 reaction centers, which is similar to photosystems in plants. This reaction center is known as the iron-sulfur reaction center. Photosynthesis in green sulfur is very similar to that of purple bacteria, but differs in several aspects and include more enzymatic reactions. The animation I have made will help explain the differences between green sulfur bacteria and purple sulfur bacteria and learn the mechanism of green sulfur bacteria. Green sulfur bacteria have two routes for electrons, both driven by the excitation of P840. Electron transfer through this complex powers the proton transport and creates the proton motive force used for the synthesis of ATP, just as in purple bacteria and in the mitochondria. The difference is, in contrast to the cyclic flow of electrons in purple bacteria, some electrons flow from the reaction center to an iron-sulfur protein, known as ferredoxin, which then passes electrons via the ferredoxin NAD reductase to NAD+. This all in all produces NADH. The electrons taken from this reaction center to reduce NAD+ are replaced by the oxidation of hydrogen sulfide, to then sulfur, then to sulfate, in the reaction that will create the green sulfur bacteria. This oxidation of hydrogen sulfide by bacteria is chemically analogous to the oxidation of water by oxygenic plants. Okay, now quiz time. Yes, I know. Get your eye clickers ready. You have 30 seconds. A pair of bacterial chlorophyll A molecules are considered the special pair. They constitute of the P870, which is the site of the initial photochemistry in the bacterial reaction center. Energy from a photon absorbed by one of the many antenna chlorophyll molecules surrounding the reaction center reaches P870 by exciton transfers. Within these two bacterial chlorophyll molecules, so close that their bonding orbitals overlap, the redox potential of P870 is shifted by an amount equivalent to the energy of the photon, converting the special pair to a very strong electron donor. P870 then donates an electron and passes it to its neighboring chlorophyll monomer, pheophytin. Green sulfur bacteria have two routes for electrons driven by the excitation of P840. They contain a cyclic route through the quinone to the cytochrome BC1 complex and back to the reaction center via cytochrome C553, and a non-cyclic route from the reaction center through the iron-sulfur protein ferredoxin. This catalyzes the NAD in a reaction, which is then catalyzed by ferredoxin NAD reductase.